Okay, hello everybody and welcome to this GCSE and A-level physics live stream. So first of all, we're going to be doing GCSE between now, which is about 7:30 and 8 o'clock. So we're going to do about half an hour of GCSE revision, all aimed at physics paper 1 that you have coming up very soon. And then from 8 o'clock onwards, we're going to be doing some A-level stuff. So hello to everybody. Hope all of you are doing really well. Now, the first thing I'd just like to say is that I do have a completely free revision guide, which is aimed at AQA, both people doing triple science or separate, and also those who are doing the combined, combined trilogy as well. So basically, for this thing here, you can download it. Inside it, there are a huge amount of bits of information that you just need to know. All of this you should be familiar with by now. So it has like the circuit symbols. I know there's occasionally a question where you need to write down the circuit symbol for a fuse. There's also the definitions all in one table. Basically you can download the whole thing, which includes a huge amount of learning checklists for every single topic. And you can basically tick this off as you're revising. If you want to get this, then it's completely free to download. I'll put the link in the chat now. But you can, of course, find this over at GCSE Physics Online as well. Okay, so today we're going to be doing some questions initially about half-life and radioactive materials. And then the second question we're doing tonight, again, is like a paper 1 topic, looking at electrical circuits and series and parallel. So this is just part of my overall revision. These shouldn't take too long to do. And then once we've done these, we'll have a go at some other kind of quick and easy questions. So, shall we begin? By the way, I hope everybody out there is doing really well. And also, if you want to find out exactly which content I'm going to be doing with A-level, and A-level down here is going to be from 8 o'clock onwards, you can go to alevelphysicsonline.com/live, and you can see exactly the questions we're going to be going through. We're going to be doing some multiple choice questions, so a range of topics from a 2021 paper, but you can download that paper and see exactly what we're doing in half an hour's time if you go to alevelphysicsonline.com/live. Okay, so here we've got a table, and it has different radioactive isotopes, the radiation emitted and the half-life. Now, none of this is information that you have to remember. You don't have to recall the half-lives of particular things, but these are just some of the common ones that could come up in the exam. Now, here we've got a graph showing the activity times 10 to the 3 becquerels, so going 0 up to 30. And as we see the time going along in years, we can see how the activity of that sample decreases. And the first thing we need to do, Danielle, yeah, half-life is a bit confusing. The first thing we need to do is we need to work out the half-life of this particular thing. Now, this is lead-210. 210 just refers to the isotope of lead that this one happens to be. So we need to look at the half-life. Now, to work out the half-life, this is simply the time it takes for half of that sample to decay, or the time it takes for the activity to drop to half of its original level. Now, initially, when time is 0, the activity is equal to 30 times 10 to the 3 becquerels. And we want to work out the time it takes to drop to half that amount, which is 15. So if we read across here, we can see at 15, we can then follow that down. That's equal to 20 years. So Matty, James, yeah, both of you correct. 20 years is the time it takes for this to drop from 30 down to 15. We could check it again. We could actually look at what the level is. After 40 years, so that's 2 half-lives, this has dropped again from 15 down to about 7.5. And so in this time period here, this half-life has gone from 15 down to 7.5. And over the next 20 years, it would again drop down to half of that value, yet again at 60, and then half again at 80, and so on. So in the same time period, it drops by the same proportion. So for this one, the half-life is equal to 20. And of course, we need to make sure we include the unit, because some of these have got half-lives of minutes or days. This one happens to be 20 years. Okay, so that's what we mean by half-life. And again, if there's anything you're not sure about, you can head over to GCSEphysicsonline.com, and I've got videos that explain all of this, and you can use those tonight and tomorrow as you're revising. Right. It then says, I can see your point as well, so just looking at the chat, AQA often use really wordy questions for half-life, and yeah, that's quite difficult. There will be some quite wordy questions, and actually the science and physics will be easy. The difficult thing is actually trying to work out from the question exactly what they're asking you. Okay, we now have 60 grams of this bismuth 214. It's initially present in a sample. And we want to calculate the mass of bismuth 214 that we left after 60 minutes. So, looking back at the table over here, we can see that this particular radioactive isotope of bismuth, it emits beta, and it's got a half-life of 20 minutes. Okay, so that's our half-life. But it says here that after 60 minutes, that's the total time, and we're going to divide that by 20 minutes. So basically, this is the total time up here. This is the half-life, and that's just equal to 3. So there's going to be 3 half-lives. So 3 times a half-life. Now, that means the 60 grams will have divided by 2 after 1 half-life. It'll have divided by 2 again after 2 half-lives, and it will have divided by 2 again after 3 half-lives. So what we really have here is 60 divided by 2 raised to the power of 3. Okay, right, so that's just the same as 60 over 8, and 60 over 8 is equal to 7.5. So although we had 60 grams initially, we've now only got 70 grams left. Okay, there we go. Hopefully that's all right. Okay, the next question then says, explain which of the isotopes in the table would be most suitable for use in a smoke detector. Okay, so for this one, you do need to have some knowledge of, maybe a little bit of knowledge about how a smoke detector works. Now, a smoke detector works, and I've got a video about this, and I've had this in one of my other practice papers. And of course, it'd be interesting to see that there's a lot of people out there who have been using my practice papers. I'm just going to have a quick look at my table of data. So yeah, quite a few people have actually seen my GCSE practice papers. There are 6 in total for paper 1. And of course, by doing these papers, you'll get exposed to maybe another 60 or 120 extra AQA style exam questions. But one of them is about a smoke detector. And a smoke detector basically uses an alpha source. And the alpha source has to have a long half-life. Okay, so basically we want something that's going to last for a long time. Now, we don't want to have something which is emitting gamma, because if it's emitting gamma, then it's going to be ionizing over a large distance. And it's the same with beta. Beta has quite a long distance, so we don't really want to use these things over here. Now, the other thing, we then have 2 alpha sources which could be suitable. Radium-226 and radon-222. Both of these emit alpha, but radon-222 has a really short half-life, and that means within a couple of weeks its activity would drop to pretty much background. So radium-226 is the right answer. So in order to get the marks for this, you effectively have to say something like, just state the obvious. Basically state which one out of all of these sources is going to be most suitable. So radium-226 is most suitable. And then of course we need to explain. And yeah, so part of it is the fact it's got a long half-life, and that means the activity is going to stay fairly constant. So we could say it's most radium-226 is most suitable. It only emits alpha, which is short range, so won't irradiate people nearby. And the other thing, I suppose, is it has a long half-life. And that means so its activity will stay at a consistent level. Okay, so there are a couple of things we could say. I think a lot of people there are saying the right things in the chat. Yeah, okay, so this one over here, it's just about looking at a table with some different radioactive isotopes and deciding which would be most suitable for that particular use. And this is something that does come up quite a lot in exams, is that although we have these radioactive sources and people often think of them as being dangerous, they do have uses depending on if it's alpha, beta or gamma radiation and which is most suitable for that particular application. Okay, the next question is to do with circuits. So we've got a circuit, we've got 3 identical bulbs in series with a 12-volt battery. Now, although we've got data given to us up here in the question, I think it's always a good idea to add this information onto the question. Right, the first one, state the potential difference across each bulb. Well, what we have is a 12-volt power supply, and we have 3 identical bulbs. So, of course, in the chat, I'm expecting lots of people now are going to start putting in what it is. Hyperslane, excellent. James, both saying 4 volts, as does Ideal. Hal N, Daniel, yeah, 4 volts. I would say that basically this 12 is going to be divided by 3. So we're going to have 12 volts. We're going to divide that by 3, and that's equal to 4.0. So I'm going to give my answer as 4.0. Now, of course, at GCSE, all of you would have got the marks. Alistair, Nathan, Matty, you'd all get the marks because you put down an answer of 4. But I think to be kind of completely correct, because that's to 2 significant figures, I'm going to give my final answer to 2 significant figures as well. Okay, each bulb has a resistance of 30 ohms at this potential difference. Calculate the current flowing through the battery. Now, there's a number of different ways that we could do this. The first thing, though, is I'm just going to write down the equation. V is equal to IR. Okay, now, James, I think, straight in there with an answer. Let's have a look. So, V equals I times R. That means the current is going to be equal to the potential difference divided by the resistance. Now, the first way we're going to do this, I'm just going to put first, is we can look at maybe one of these bulbs here. So I'm just going to put some information that we know that there's 4.0 volts across that bulb, and we know that it's got a resistance equal to 30 ohms at that potential difference. And therefore, the first way of doing it is saying, well, just thinking about that one particular light bulb, the potential difference is equal to 4.0 and the resistance is equal to 30, and 4 divided by 30 is equal to 0.1333. So my current is 0.13 of an amp. Okay, that's the first way of doing it. Now, the second way of doing it is by thinking about the total potential difference across all of these light bulbs, and also the total resistance of all of these. So the second way is to say, okay, between these 3 lamps, we've got a total of 12 volts across them all. Now, their combined resistance is going to be equal to 30 plus 30 plus 30. So that's 30 plus 30 plus 30, and that's then equal to 12 over 90, and that's also equal to 0.1333 and so on. So it doesn't matter if you look at just one individual lamp and the potential difference across that lamp and its resistance, or the other way you can do it is you can look at the total potential difference across all 3 of them, divide that by the total resistance of all 3 of them, and again we'll get the same current. And therefore, for a question like this, there's more than one approach. But effectively what we have is a series circuit, and that means there's only going to be one loop where the electrons can move around, and there's going to be the same current everywhere in that loop. Okay, number 6, 6.3. The student adds the switch as shown in figure 8 below. So again, they've got the same circuit. We now have a switch here. State and explain what happens to the brightness of each bulb compared with the brightness in circuit 7 when the switch is closed. So what we've done is we've basically closed that switch. Now we still have a 12-volt power supply, but here what we've actually done is we've kind of short-circuited it. So if we think about electrons leaving this, they're going to go around here, they're going to go through this lamp, they're going to go through this lamp, and at this point they're going to go down the path of least resistance, which is this bit of wire here. So there's going to be no electrons flowing that way. So what we have over here is a short circuit. And that means whatever current is going along here is going to go up this way and back into that. Okay, so effectively there's going to be no current in this part of the circuit. Now the other thing then is that if that's a 12-volt power supply, and we've only got 2 lamps now, and it's kind of short-circuited up here, then that means there's going to be 6.0 volts across this one, and there's also going to be 6.0 volts across that one. So what we can see now is that that same potential difference has been shared between 2 components rather than 3. So, state and explain what happens to the brightness of each bulb. So we can say that bulb 1 and 2 get brighter, and the reason is that because they now have 6 volts across them rather than 4 volts before. So that's the first thing. Okay, somebody heads is saying, you're doing A-level but kind of confused. Why do parallel circuits not short circuit if it takes a path of least resistance? Well, effectively, what we say is with ideal wires, this has a resistance of 0, and therefore it's, basically it's only when you've got a resistance of 0 that we have a short circuit. If there was a resistor here, we'd have current going both ways around this part of that circuit. Okay, so bulb 1 and 2 get brighter because they now have 6 volts across them rather than 4, like we had before. Bulb 3 goes out. As the switch short circuits that part of the circuit. Okay, hopefully that's all good. Alright, so that was the second question. Now we've got about 12 minutes left. I'm just going to go and open a window because it is really hot in my office. And what I thought we'd do is use an app. Okay, now there's an app that has a huge amount of multiple choice questions. I think I used this last year when I did some live streams. The app is called Fizz Quiz. I was going to write that down. Oh, I need a bit of paper. Okay, so Caitlin, let's have a look at your question, sorry. So if there's a path where there's only one resistor, will it still take both paths, or only the path without a resistor? Okay, yes, so if you had a circuit, okay, now imagine we've got a circuit where you've got a power supply and there's a resistor. All of the electricity is going to be going this way around that circuit. If you put in a parallel loop with a resistor, some of the current is going to be going this way and some of the current is going to be going that way. Okay, but if you had at any point a loop where there was just a wire, effectively that's got a resistance of 0, and that means all the current is going to go through this and none of it's going to go around this part of the circuit which has a much higher resistance. So this is what we call a short circuit, and effectively there's going to be this loop in the circuit like this, where if we have ideal wires we know that the resistance is 0 and therefore the current, because R is equal to, or the current I is equal to V over R, this is going to be equal to V over 0, which is kind of infinite. Okay, now of course that's if we had ideal wires, but in reality all our wires still have some resistance. But basically, if you've got this loop here with just a wire, then we assume there's no resistance and it's a short circuit. Okay, right. What do I recommend doing tomorrow night as revision before paper 1? I reckon the night before paper 1, you want to be making sure that you do get a restful night, but we'll use this app here. So the app is called, where is it? I've got it somewhere. I've got too many apps, one sec. Okay, so the app is called Phys Quiz. Okay, again, I'll just write that down for anybody who might want to download it. So this one here, the app is called Phys Quiz. Okay, I'll put that by the phone. And what we can then do is we can just choose some questions to have a go at. So obviously, play along at home. What should we do? Energy, electricity, particle model, or atomic structure? What do you want to be doing? Okay, so this app here is called Phys Quiz. It's not mine, but I think it's really useful. What do we want to be doing? Electricity, says Matty. Particle model, please. Okay, Hyperslane. Electricity, says Hal. Let's see what most people say. So at the moment we've got more electricity than anything else. Atomic, says Sala. I'm afraid I can't make all of you happy, but obviously you can download this yourself. Uncertainties, electricity. Okay, let's just do electricity. So let's do series and parallel circuits. Okay. Hopefully you can see all of that. So in this circuit, if A1 reads 2 amps, what does A2 read? So is it bigger than 2 amps, smaller than 2 amps, 0 amps, or 2 amps? So is it, which one of these here is it? So Hyperslane says 2A, Matty 2A, James 2A. Okay, should we go for 2A? Correct, nice. Okay, where should the voltmeter go? Position 1 or position 2? So where should the voltmeter go in this circuit? Position 1 or position 2? A lot of people are saying 2, 2, 2, 2, 2. So it should go in position 2 because the voltmeter always goes in parallel. Which side of the battery is positive and which way does current flow? Okay, so there's 2 things here. So if you want to just put maybe A, B, C or D, because I know there's like 4 answers here. So if you want to just put A, B, C or D in the chat, which side of the battery is positive and which way does the current flow? Okay, and when we're talking about current here, we're going to talk about conventional current. So people are saying left and anti-clockwise. Yeah, so the left-hand side, the taller one is a positive, so that's the left. And it's going to be going from positive to negative, which in this case is anti-clockwise. So B is what people said. Yeah. Yomne. Hi, so just wondering what's the range of size of units that we need to know, like nano to giga. I would say for GCSE you need to know micro, 10 to the minus 6, milli, 10 to the minus 3. Then you've got kilo, mega, giga, and tera. I think they're the most important ones. Okay, a battery runs down because it runs out of what? So a battery runs down because it runs out of, what do you reckon? Energy? A battery runs down because it runs out of, I reckon it runs out of energy. Yeah. There we go. That was a tricky one. Okay, look at this. Determine the value of V. So we've got a 9-volt battery, sorry, a 9-volt cell. We've got 9 volts across R1. R2, we don't know the voltage across it or the potential difference. So what would it be? Sarah says 9, Hyperslane says 9, James says 9, Alistair 9, Ben, hi Ben, Hal, Matty, Bramble. I know some of you are A-level people, so this should be okay. 9 volts, perfect. What happens to the total resistance in the circuit when switch S is closed? Okay, this is good. So this is kind of what we've done already. I would say that when S is closed, it's going to reduce the value of this, and that means it's going to, the total resistance is going to decrease. Yes, there we go. Because now we've short-circuited that. So rather than having a resistance of 6 ohms, when we shut the switch, we short circuit this part of the circuit, and that means the overall resistance is now 4 ohms for that circuit, so it goes from 6 down to 4. In a circuit, the current leaving the cell is greater than the current returning to it. Okay, A, B or C, what do you reckon? Never true, always true, or sometimes true? In a circuit, the current leaving the cell is greater than the current returning to it. People are saying A, never, A, yeah, people are saying, I think the right answer, this one's not as many people are answering, so A, never true. Okay, win streak. So basically the current leaving must always be the same as the current going back into it. Yeah, Kirchhoff's first law, looking at the sum of the currents at any point in that circuit. Determine the value of the current I. So what would be the value of I? Well, we've got a parallel circuit. To be honest, we can ignore the bit at the bottom. We know we've got 6 volts across a 4 ohm resistor, and V equals IR, so I equals V over R. So that would be 6 over 4, which would be 3 over 2, so that would be 1.5. Hyperslane, yes, straight in there with that. Bramble saying C, James saying C as well. That is the right answer. What happens to the brightness of the bulb B when switch S is closed? So A, B or C. What happens to the brightness of switch, and this is going to be assuming it's like an ideal cell. What happens to the brightness of bulb B when the switch is shut? So people are saying stays the same. Jack saying C. It's going to stay the same because even though there's going to be a current now going to A, that we're going to have the same potential difference across B at all times, and therefore, because we've got parallel parts of that circuit, it's going to stay the same. As you add more light bulbs in parallel, then the brightness of each one stays the same. Okay, right, which circuits are equivalent? So I would say that which of these circuits are the same? So we've got a couple of resistors, R1 and R2. We've got R1 and R2 in parallel, R1 and R2 in parallel, R1 and R2 in parallel, R1 and R2 in parallel. So I would say all of them are the same. It's exactly the same. So A, B, C and D are all identical circuits. Let me just put that up on the screen again. Hopefully you can see that. Okay. Which circuit has the lowest total resistance, A or B? So looking at these two circuits, both of them just have 2 ohm resistors. So we've got 2 ohm resistors in parallel, 2 ohm resistors in series. Which of these has the lowest overall resistance or the lowest total resistance? The answer, as everybody has said, Hyperslane, Sala, James, Matthew, Bramble, Yomna, Josh, Music and Media, Alistair, Daniel, all of you saying A, perfect. This would have a combined resistance of 1 ohm. That would have a combined resistance of 4 ohms. What happens to the total resistance in the circuit when switch S is closed? So, what happens to the total resistance in that circuit? So, the total resistance, people are getting the right answer there. The total resistance decreases. Fantastic stuff, everybody, because now we have more loops in that parallel circuit, so it's going to decrease. Okay, all the bulbs are identical. How much current goes through each light bulb? So we've got a 12 volt supply, we've got 2 amps on an ammeter just near to that cell, and we have 4 identical light bulbs. What is the current that goes through all of those? The answer, Hyperslane, again, correct answer there, 0.5 amps. Because you've got 0.5 plus 0.5 plus 0.5 plus 0.5, which is 2 amps. Yeah, and it's split equally, heads, exactly, good stuff. Determine the value of V. So what is the potential difference across that component? I'd be looking at V equals I times R, just writing that down every time you see an electrical question. We know that current I is 3, the value of R is 2, and therefore V equals IR, so 3 times 2 is 6 volts, and that would just give us this one here. Excellent stuff. Right, another minute of this, and then we're going to go on to A-level. What happens to the total circuit resistance when resistors are added in series and in parallel? So in series it's going to increase, and in parallel it's going to decrease. So I would say number 1 is correct. A. Right, so for all of you GCSE gang who are watching this at the moment, you can download this app. It's called Phys Quiz. Definitely worth playing around on, and you get a lot of questions in a short amount of time. The app is called Spirit Phys Quiz. Okay, hopefully that's quite clear. So you can download that. It's completely free to use. I think you can actually pay for extra questions, so that's well worth doing. And of course, supporting the developer who's made that. But yeah, there we go. Some GCSE stuff. I will be back tomorrow doing some more GCSE stuff. But of course, if you are a GCSE student and you need more help, I do have hundreds of videos where I cover everything for GCSE physics, and if you want to find out more, go to gcsephysicsonline.com, my website. Everything's organised there. That means you can find any video you need tonight or tomorrow morning as you're starting to panic. And of course, you can buy access to extra videos, you can buy my practice papers, and even though some of that might be a bit late for paper 1, there's plenty you can do in the run up to paper 2. 7:30 tomorrow, Yasmin. As always, 7:30 for my GCSE part of the live stream. Okay, right, so now we're going to be doing some A-level stuff. For the A-level lot, right, let me just zoom out. I've kind of gone a bit weird with the camera. So tonight, these questions, have I gone out far enough? There we go. Right, tonight, these questions are for the 2021 OCR A-level paper. Now, although it's an OCR paper, obviously the OCR people in there, actually, all of you out there, let me know in the chat if you're A-level, if you are OCR, WJC, Edexcel, AQA. Now, of course, Theo, this isn't going to be perfect for AQA people, but all of this stuff here is good physics, and it's just a good way to look at lots of different topics. Oh my God, there's so many people here. Okay, so most of you are AQA. So even though we've got an Educast, Ben, fantastic. You're like a rare breed. There's not many Educast people. There's only about 500 or 800 of you in the country. So you can see that most people are AQA. Of course, OCR lot, you should know this. This is all going to be perfect for you. AQA, this is all going to be good for you. And most of this is still coming up in paper 1, if not paper 2, which is only a couple of weeks away. So I'm not forgetting about you AQA people. In actual fact, if you haven't already been there, then I do have work solutions on PMT for all of the AQA multiple choice questions. I've written out my work solutions. You can download them for free over at Physics and Maths Tutor. I know you'll have done the paper already, Mardy, but you know, yeah, there's probably other stuff I've done that you haven't seen yet. Right, so an object is moving in a straight line. The displacement against time graph is shown below. Which point does it have the greatest speed? So I would say, of course, all of you, please do play along at home if that's what you're doing this evening. I would say it's got the greatest positive velocity at A. It's then going to be stationary, then it has a negative velocity. But I would say the highest speed is going to be at C, and that's where we have the greatest magnitude of its gradient. Good. Which of these represents the smallest multiplication factor? So for this, all you need to do is think, okay, femtos times 10 to the minus 15, micro times 10 to the minus 6, nano is 10 to the minus 9, and a pico is 10 to the minus 12. Okay, so it's often useful to kind of write your own notes to the side of it. I think yesterday as well, I found it useful to use pencil, or I probably should have used a pencil at times. So which of these has the smallest multiplication factor? It's femto, 10 to the minus 15, and therefore the answer, as everybody is saying in the chat, so Dev, Theo, Yasmin, Ibtisam, Bramble, Spirit, yeah, there we go, femto. A femto is just a really small unit, maybe used when you're looking at particle physics. Okay, the table shows some data for a car travelling on a straight road with an initial speed of 13 meters per second. So a question like this, I would say don't look at the answer. Instead, think we've got a motion question. What's the magnitude of the deceleration of the car during braking? I'm going to write down Suvat. Okay, we know the initial speed, u, is equal to 13. It's going to stop, so v is 0. We do know the distance. The braking distance is 14 meters, and that's obviously meters per second. And we don't know this. So what we have is a suvat thing, and therefore, as I think Jack has already put down, we know that v squared is equal to u squared plus 2as. We want to find the a, so v squared minus u squared over 2s is equal to a, which is equal to, just going to put the numbers in, 0 minus 13 squared over 2 times 14, so that's 169 over 28, which is, let's have a look, 6.03, and therefore 6.03 or minus 6.03, and that means the answer is going to be C. So for this one over here, I would say don't get distracted by the answers. You see it's a motion question. Most of you are doing A-level maths. You know suvat. This is easy. Just work it out in the normal way. Don't take shortcuts, and that means you're much more likely to get the right answer. So there we go. By not taking shortcuts, still showing my own working out for my own sake, that allowed me to get to the right answer. Okay, the next one, the freezing point of ethanol is 159 Kelvin. What is 159 Kelvin in degrees Celsius? Well, basically, it can't be that one because you can't have minus 432. We know it's not going to be above 100 degrees. We know it's not going to be that one, so the answer must be B. In actual fact, we know that 273 take away 159 is equal to 114. Okay, so this one over here also is equal to, sorry, 159 take away 273 is equal to minus 114. Okay, so for this one over here, almost by common sense, it's 114 minus 114, and the answer is B. 159 minus 273. Perfect. Iptisam. Excellent. Okay, all good so far? This is easy. I think all of you are going to be getting A stars at this rate. Okay, now this one over here is something which is specific to OCR. So if you are OCR A, I know lots of you are, you know this. If you are AQA, do not worry about this. This is not something that comes up on paper 1 or 2 for AQA. Okay, so this one over here, let me just look at my notes. We know, of course, that the Hubble's constant h0 is equal to the recessional velocity over the distance. Okay, and we also know that V over C is equal to delta lambda over lambda. Okay, so that's the velocity over the speed of light of that recessional velocity is equal to the change in wavelength, delta lambda over lambda. Now, we could put these two together to say that, let's make them both equal to V. So we can say that dH0 is equal to C times delta lambda, which I guess would be lambda 2 minus lambda 1 over lambda 1. Okay, now we want to get Hubble's constant on its own, and therefore H0 is equal to C times lambda 2 minus lambda 1 over d lambda 1. And again, I don't know which one that is. Is that any of these? Yes, it is. It's this one up here, the first one. So again, my approach a lot of the time is to do the working out and then look at what the answers are. So my answer is A, and that means I'm not being distracted by the other things over here. You don't need to know about Hubble's law at GCSE. This one here is an A-level thing. You can see that between 7:30 and 8 we did GCSE, and now 8 o'clock onwards we're going to be doing some A-level. Okay. Is there a possibility of a level of response 6 marker for all of the papers or just paper 3? Allerton jumps revamp. Is that like mountain bike jumps or BMX jumps, is it? I don't know, to be honest. I think there is a possibility that you could get longer written answers, definitely for 4 marks on paper 1 and 2, but I can't remember off the top of my head. Okay, for a simple harmonic oscillator, the maximum speed is Vmax, when the amplitude is A. The frequency of the oscillations is F. What expression is correct for this oscillator? Well, we know that Vmax is equal to omega A. That is just something you need to know. And of course, omega is just going to be equal to 2 pi f. So we can put this back in there to say that Vmax is equal to 2 pi fa. And again, now we've done the work, we can look at what the answers are. 2 pi fa, so here the answer, I think, is B for number 6. Great stuff, everybody. 2 pi f, yeah, Ibtisam, Bramble, Dev, excellent, excellent. Okay, not too bad so far, is it? This one, though, I thought was a little bit tricky. There's a load of stuff here. I would say if I saw a question like this, it looks like there's a lot to read, so I just skip it and move on and come back to it at the end. Okay, we're not going to do that. We're going to keep it in order. So what we have is a graph of force over here in newtons, and we've got the radius in meters. And we want to know what the area represents. Now, whatever the area is going to be, it's going to be equal to some kind of force times some kind of distance. Okay, and we know from work done is force times distance. We know that means the area must have the units of joules because it must be some kind of energy. Okay, and that means it cannot be the centripetal force because the units don't tie up. It couldn't be the impulse of the force acting on Mercury because that's in Newton seconds, and here we've got newtons times meters, so it's going to be an energy. So it's either gravitational potential or kinetic energy. So at the moment, so Dev, for this one here, whatever it is, it's either going to be B or D. It can only be something to do with energy because the area under that line is equal to the force times distance in meters. So it's a Newton meter, which is also a joule. Are these live streams going to be every day until paper 1? Yomna, yes they are. I've been doing live streams for a month now. If you want to find out anything, then you can go to alevelphysicsonline.com/live, and you can see all of my past live streams. And also on YouTube, you can just search. You'll see that there's like a colour change, which is actually due to it's going to be some like emission spectra and some kind of hydrogen lines. You'll see that eventually in the coming weeks. Okay, so people think it's B or D. The answer is actually B. So this is about the change in gravitational potential energy of Mercury as it moves from one position to the other. Okay. Now, of course, we do know that F equals GMM over R squared. Okay. And what we have here is the area is equal to FR. So that's going to be equal to the force, which is GMM over R squared times R. And that is equal to GMM over R. And that's therefore to do with the gravitational potential energy of that and the change in gravitational potential energy. Okay, right, this is nice. Again, do not look at the answers. Okay, so what is the weight of the object? We've got an object, we've got a tension in 2 cables, and if we think about the forces on it, the force down is due to the weight, and that's going to be equal to the tension in this cable plus the tension in that cable, but they're identical, and therefore it's going to be equal to 2 times the tension in each, which is 2.0, and we're going to look at the vertical component of that tension, which is cos 35. So therefore it's just the same as cos 35 times 4, and the weight is equal to 3.277. So I would say that's going to be this one over here, and therefore the answer is D. So yeah. And let's see what people have said. Loads of people are doing the right thing. Joel saying 2 cos 35 times 2, perfect. MW cryptic, 2 cos 35 times 2. Dev, 2 times 2. So yeah, okay, not just a little mistake there. D says Harry, D says Joel, 4 cos 35 says Riptide Kills. D says Ibtisam. H7 of Polo, Newtons everywhere. It's your names. Some of your names are really difficult to read out quickly. Okay, we then have a piston that has a fixed amount of trapped ideal gas. We know that there's a pressure, a volume, the temperature is T, the mass of the atom is m, there are n atoms of the gas, the Boltzmann constant is k. What quantities are required to determine the root mean square speed of the atoms? Okay, so I would say for this, the equation that we can select from our equation sheet is that PV is equal to a third nm c bar squared. So the quantities needed are, we need to have P, we need to have V, we need to have N, and we need to have M. So I would say for this, the answer is going to be this one over here, which is D. Yeah. Madame Pinky II, hi sir. Yeah, got a projectile question. That is the vertical drop time the same as the horizontal drop time? Yes, it is. The time down is the same as the time across, always. Yeah, as Munchma Quatchi says as well. Yeah. Okay, now some of these questions might be paper 2 questions for AQA, but these are some paper 1 questions from OCR, which I can show without any kind of copyright restrictions on YouTube. Okay, I'm just going to go and shut the window. One sec. Just some horrible kids outside on scooters. Okay, right, here we go. Okay, so an object of mass 0.12 kilograms is lifted through a height 0.6 of a meter at a constant speed of 3 meters per second. What is the minimum power needed to lift the object? So I would say for this, there are a number of ways of approaching it. One way to do it could be to say that force is equal to power times velocity, and therefore the power is equal to the force divided by the velocity. Now the force needed to move it at a constant speed is going to be equal to its weight divided by the velocity, and its weight is equal to mg over v. Is that right? Have I made a mistake there? So that would be 0.12 times 9.81 divided by 3, which is 0.3. I've made a mistake. Okay. Right. A better way to do it would be to say that the power is equal to the change in gravitational potential energy with time. And that's going to be equal to mgh over t. Okay. Which is equal to mgv. So that's going to be equal to 0.12 times 9.81 times 3.0. Okay. Was I right? P equals FV? Oh yeah, P equals FV. That's what I should have said, shouldn't I? That's the same thing as this down here. Okay, I think I just broke the wrong thing down initially. It's very hard to kind of talk and think about physics at the same time. But there we go, the answer is 3.53. And that means the answer is going to be closest to C. So that's it. People are asking, what did Megawatt say? Yeah, it is a wrong way around. Yeah, I should have said power equals force times the velocity. And of course, the force is going to be equal to the weight. In actual fact, the height doesn't matter because we're looking at the amount of energy transfer per second. And therefore, the total height moved is actually irrelevant. So the answer for that was C. Okay, this one's nice. Again, this is a paper 1 topic for OCR. AQA, this is more of like a paper 2 question. So let's have a look. Kepler 60 is a star with several planets orbiting it. The 2 outermost planets are 90G and 90H. We've got 90G as an orbital period of 210 days and is 0.71 from the centre of the star. Kepler 90H is 1.01 from the centre. So what is the orbital period of Kepler 90H? Now there's a lot of information there. Here's the star. We've basically got this one and this one. Okay, so we know that G is this one over here, and out here we're going to have H. We know that that distance is 0.71 and this distance is equal to 1.01. We know the time period for this is 210, but we don't know the time period for that. So I do think it is really important. Yeah, the word Kepler comes up a lot, doesn't it? How many times does it come up? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the word Kepler does come up a lot. Now, of course, we do know that t squared is proportional to r cubed, and that means tg squared over th squared is equal to rg cubed over rh cubed. That should make sense to you. So of course we know that t is proportional to r cubed, then this t squared over that t squared is equal to that r cubed over that r cubed. We want to find th squared, so th is going to be equal to tg squared times rh cubed over rg cubed, and then it's going to be the square root of all of that, isn't it? Okay, hopefully that's all right. Am I muted? I don't think I'm muted. You can't hear me. Can people hear me all right? I think you can hear me. Cool, that's good. Right, okay, so basically that's what we need. So therefore we can say that, let's say rh cubed, so we've got 1.01 cubed divided by, so I'm just trying to work this out, and then we times that by 210 squared, 356. 356. Okay, so the answer is 356, and therefore the answer is C. Okay, right. Oscillations can either be free or forced. Which of the following is an example of a forced oscillation? By the way, King, thank you so much for your £2 donation. I do appreciate the donation. Thank you very much. Oscillations can be free or forced. Which of the example is a forced oscillation? Well, if it's a ball rolling to and fro on a curved track, then that's just a free thing. A loudspeaker oscillating producing a continuous note is a forced one because it's forced by that alternating current in that thing. Oscillating mass, pendulum just going side to side. These are both free things as well. So for the answer for this one, as people are saying, well done to Joel, to Madam, Bramble, Music and Media. B is the correct answer. Thank you very much. Right, we've got a few more questions to go. Here we have the force against extension graph for a material being stretched. What is the best estimate for the energy stored in the material when the extension is 10 millimeters? So here we have force times a distance, and therefore the area underneath that line is going to be equal to the energy stored. Now, of course, what we have is if we were to look at the total area of that square, that would be a force of 20 times 10 times 10 to the minus 3. And that would be equal to 20 times 10 to the minus 3. Sorry. That would be equal to 0.2. So the whole square is equal to 0.2. If we were to look at half that square, so if we had this triangle over here, how do I know to use triangles or trapeziums? Well, I'm just going to guess. If I had the triangle, that's going to be a half times 20 times 10 to the minus 3, and that's equal to 0.1. Now the area in purple is going to be bigger than 0.1 and smaller than 0.2. So that means it cannot be 0.7 because that's too small. It can't be 0.1 because that's the area of a triangle, and it can't be 0.2 because that's the area of the whole square. So it must be this one over here, which is 0.13. So the answer for this is C. Okay. Now you could do that by counting squares, but everybody hates doing that. You could have estimated it maybe by using this triangle, and then you've got this kind of shape over here, and this shape over here, and this one over here. But it's really a kind of guesstimate. Your teacher, maybe Madam Pinky, was, I mean, Counting squares is good, but it's time consuming, and this is just an estimation, and therefore we know it's bigger than 0.1 and smaller than 0.2, so it must be somewhere in the middle. Okay, a ball of mass m is falling vertically through the air. The total force on the ball upwards is F. The force F is less than the weight of the object. Which expression is correct for the acceleration of that ball? Now we do know that the resultant force, so I'm going to call that the resultant force, is equal to the mass times the acceleration. Now the resultant force is going to be equal to the weight of the ball, take away F, which is the force that we have over here, and that's going to be equal to ma. And we know that the weight is equal to mg. So mg minus F is equal to ma, and that means we can say that mg minus F over m is equal to a. Okay, so we just rearrange that to make a the subject. Easy. People are saying mg minus F over m. Yeah, the answer is B. That was okay, wasn't it? Loads of people are saying B. Riptide Kills, Ibtisam, we've got Bramble, Terry, Foxticus. Yeah, right. Go back to question 7. I can't find where I've put it on the floor now. But what you can do at the end of the stream is if you go back on the stream, if you want to redo any questions and have a look on the stream, and you can go back to the question that you need afterwards. Okay, the parallax angle for a star is 0.015 seconds of arc. What is the distance in parsecs of the star from the Earth? So if we've got, we basically know that 1 parsec, basically 1 parsec is when the angle is equal to 1 second of arc. Okay, and so basically if you've got 1 divided by 0.015 second of arcs, that's going to be equal to 66.7, and therefore the answer is A. There we go, A. Right. Some good questions people are asking. Is this an OCR question? Yes, it is, and therefore if you're doing AQA or EdXL, you do not need to know about this for paper 1. Do I go live every day? Hello, Richard. Yeah, I've been doing lots of lives. They've been on YouTube for like the last, I think, month, 5 weeks now. Basically, ever since Easter, I've been live kind of 4 or 5 days a week. If you want to catch up with my previous live streams, then you can head over to alevelphysicsonline.com/live, and then you can see all of the live streams, all of the topics. You can download everything that I've done. So that's all there, and that means you can like look at anything that you want to over the next couple of days. Right, so there's a big load of kind of questions up here. Okay. Yeah. Okay, so young talent, how to approach multiple choice questions of this format. Okay. What is something then? Another thing is E. So I can't really understand the question. Okay. I would say my approach to multiple choice questions is if it's a long question, don't bother reading it. If it's too much information there, just leave it till the end of the exam. So just maybe circle a question, come back to it later. I would say if it's another kind of question where there's lots of different numerical answers, don't look at the answers until you've done your own working out, and don't forget that you can still draw a diagram, put down your working, and that can help you get to the answer. Okay, yeah. What's the value that you need to remember for a fuse? Okay, in material dispersion in optical fibres, how can the waves have different speeds when they're all electromagnetic waves? Okay, so basically, even though you might have electromagnetic waves, they all have a different speed in glass, and different colours of light have a different speed, which is why we get dispersion, and that's why you see a rainbow being formed, maybe through a prism. It's because even though they're all electromagnetic waves, different electromagnetic waves will have a different speed in that material because they're not travelling in a vacuum. Okay, okay, we've now got somebody, not totally serious. You're not seeing GCSEs at A-levels, but yeah, now you're in your 3rd year as an engineer. Awesome. Do you think the exam will be super easy like last year due to the equation sheet? For GCSE, I don't think it's going to be super easy. I reckon, though, that there will be lots of easy questions that seem too easy, but I suspect they might have written some of those questions before the decision had been made about having equation sheets. So don't forget there are lots of easy marks in the GCSE exams in particular. Right, for everybody else out there, so potato sandwich 58, although I went through some OCR questions, they're still suitable for Edexcel, a lot of the topics that I've been covering. But of course, it's difficult to do everything like the night before the exam and to make it specific to exactly the bits of help that you do need. So I would say if there's anything that you need help with, then do go to A-Level Physics Online, have a good look around. I've got videos that cover all of the Year 13 content. And basically you can teach yourself pretty much any bit of A-Level physics from my website, and there's more questions there that support Edexcel and other things like that. Yeah. Right. I reckon that's it. So for everybody, I will be back tomorrow. I'm going to be doing some questions, again, more multiple choice questions, suitable for paper 1, aimed at the OCR paper, just because I can't show AQA papers on YouTube because of copyright and YouTube restrictions and things that could come into effect. So yeah, if there's any other questions that you do have, though, I will be back here tomorrow night. I'll be doing GCSE from 7:30, A-Level from 8 o'clock, and of course I'll be here every night this week helping you prepare for practice for your real paper 1. Yeah, thank you everybody, and good night.